morning, all. Sojan James here from Axia. So this talk is about writing Rust bindings for threadx, and just to walk you through the steps I followed when I wrote the Rust bindings for threadx. I do have to thank Florian for giving me the nudge to submit this proposal. It wasn't an idea, but thank you for that, Florian, and thank you for those who were responsible to do the selection. So about me, I've been programming Rust since 2018 on Linux and on embedded devices. I've been a C programmer since 1999, also C++, but I've completely forgotten it since I've started Rust. And I've been doing system software and embedded software all my career, and I've been trying to evangelize Rust in the automotive domain for some time. So in my normal day job, that's what I do. I build software for automotive digital cockpit systems, and I've been doing that for about 15 years. And I think I earned my Rust unsafe license after doing the Rust binding for Cyclone DDS, where I really had to go through the Rustonomicon, understand, wrote my first future, and also a whole bunch of unsafe code dealing with callbacks coming from the C API. I use Rust in microcontrollers, Linux applications, web services, and very recently started using it for web front-end as well. I'm not a front-end developer, but some hobby projects, and I'm really liking the threadx-sys web framework for the front-end work. Not too active on social media, but a little bit of Twitter noise. I have a GitHub as well. Axia Technologies is where I work. I have to thank Axia for allowing me to bring me here and do this talk. And we develop software for future mobility, digital cockpits, and clusters. We specialize in AUTOSAR, Linux, Android, and QNX, mostly on the digital cockpit or infotainment or telematic spaces. And we work with leading OEMs and tier ones for specialized software solutions. We're headquartered in Trivandrum. That's the southern state of India called Kerala. I work out of Bangalore offices in India. Goals for today. Why embedded Rust, or rather, why Rust for embedded devices? A little bit about threadx. I'll walk through different steps of developing a Rust binding for threadx or anything else, and some next steps, what we can work on. A very quick demo on an STM32, and hopefully some time for Q&A. I lost some time in setup, so I'll try to move fast. So why Rust for embedded? I think that's obvious. Thankfully, it's a good thing to talk on the second day. I could take out some slides. So just refer to yesterday's talk. I don't think I need to preach to the choir here. But I do have to call out some great tools, and specifically ProBars, deferred formatting. And the way it all comes together is unlike another environment, right? So it's funny that the development environment I get on this like $10 hardware plus debugger plus all the tools is far better than what I get on the commercial tools I'm buying from famous vendors. It's just sometimes ridiculous. I'd like to summarize my experience with Rust with this sentence: tread fast, tread boldly, and tread safely. Right? So that's the tagline for the automotive OS that we are building. And I think this is a good summary of my experience with Rust. Eclipse threadx is not a new kid on the block, even though I heard about it just last December. It is a vendor-neutral, open-source, safety-certified RTOS, founded in 1996 by a person called William E. Lemmy of Express Logic. And over the course of a decade or more, It has been used in many industries. It has been certified SIL 4, ASIL D, medical class, whatnot. And it's truly battle-tested. And you'll see it in the code as well. It has been written with certain, a lot of discipline. It was acquired, or the company was acquired by Microsoft, I think, in 2018. And then last December, Microsoft made the announcement that they're contributing threadx to the Eclipse Foundation, and it's going to be MIT license. So that's some background of threadx. And you can imagine there is quite a bit of wisdom of 18 years of development, that too in a commercial environment, not in an open source environment. So that they have been working under constraints, and it hasn't, let's say, gone out of control in terms of volume of code. It's really nice and tight. There are alternatives, of course, in the same space. Just to pick two, because I know them. One is the Zephyr OS. It's called the Zephyr project. It is supported by the Linux Foundation. A lot of hardware support, great documentation. It's got a large community as well. A lot of momentum on the Zephyr project. And then there's, of course, FreeRTOS, supported by Amazon. Very popular with hobbyists. It also supports a lot of hardware architectures. Again, great community and documentation. They both work fine. But why threadx? So I think with the Rust binding, it's not just about the language. You do have to think about the build system. You do have to think about the tools along with it, the crate ecosystem. All these are extremely important. Finally, the question is, who's in the driving seat? As I think Tim and Florian put it yesterday, who will be the driver? Is it Zephyr who's going to be the driver, or Cargo? Or rather, Zephyr uses a build system called Vest over CMake. So is it Vest that is going to be the driver, or is it Cargo that is going to be the driver? So I want to use Rust as a primary environment. So I wanted Cargo to be the driver, not the Zephyr tools, or not the FreeRTOS tools. Try to generate as much as possible, because when you had code bindings, there's a chance for errors, and also keeping updated to the source code is difficult. So I wanted to make sure that as much as code as possible is generated to reduce errors and reduce duplication. So why threadx? Just some snippets from the threadx code base, assembly, and some C code. It is modular. It's got a very modular build system. Clean code with pretty high signal-to-noise ratio. And I'm not kidding. I believe every line is commented with very nice, clear description of what's happening. And I did take a lot of samples, and that has been the case. It's safety certified. Yes, certified in a different context, not in the open source context. And I think Eclipse is definitely working on how that can be certified in open source context as well. But you can see that discipline of certification in the way the code is written and how it is commented on. So it's generally, it's a very subjective comment, but I felt good looking at threadx code when you compare it with the other code bases. There's a good separation of hardware agnostic and hardware specific code. The entire application is statically defined. Zephyr also uses that approach. And very simple API. It's got block and byte allocators, mutex, queues, semaphores, threads, tracing, and performance measurements, which is actually pretty interesting because I don't think the others have tracing and performance APIs built into the OS API. That's pretty nice. And my favorite is limited use of C macros, because macros are a pain to deal with when you want to connect to Rust. And the standard build system coming out of the repository allows you to build the whole RTOS as a static library and you link it with Rust. It's just perfect for what I'm trying to do. So typically when you build a Rust wrapper to a threadx library, you would go with the following steps. You would first figure out how to compile that library, or in this case, threadx. That problem was solved for me because they use CMake, and it just worked out of the box. And then you would build a -sys crate, in this case, the threadx-sys crate, which is dealing with downloading the threadx code, configuring it, compiling it, and generating the library. Plus, it would use bindgen to create the Rust definitions, or the unsafe code, the unsafe bindings to the C API. And then you would build your rusty, nice, safe Rust bindings. That would be the threadx-rs crate. And then finally, your application ideally would only use that rusty crate, or threadx-rs in this case, to develop the application. The hardware I used was the STM32. This is the little brother of, I think, the hardware which Josh spoke of yesterday. It's not so expensive. It's really cheap, and you carry it in your pocket. The whole set maybe under $10. Debugger, ST-Link plus the hardware. So available on AliExpress. It's a 32-bit Cortex M3, and it's got a whole of 20 kilobyte of RAM and 64 kilobyte of flash. It's got I2C SPI. And one nice thing is it's got CAN, which not too many people know. The USB device can also be configured as CAN. Drop a CAN PHY, and you have CAN. It's also called the blue pill. OK, so the embedded Rust application, that's the starting point. What do you do? Well, we have a whole bunch of resources to build a simple Rust application on an embedded device, thanks to the Embedded Rust Working Group. So much of fantastic material and nice tools from Ferris. I think def-FERD formatting is from Ferris. ProBaris is another project. But they all come together very well. And you can quickly build a Hello World application to boot on your microcontroller. I think just maybe in an hour, you should be up and running. Nice stuff in Ferris Systems training. Pretty much follow that. There's also a template you can just use cargo template on and a cargo generate on and have a Hello World up and running. The next step is to deal with the threadx itself, right? So writing the threadx.sys and doing the compilation. And there's some things you have to be wary of here. But maybe a side note on the word unsafe. I find it a bit unfortunate that this term unsafe was used in Rust, because I've had many conversations where people say, oh, Rust is not good because it's got unsafe code, while they're using C or C++ in their daily life. And then you have to explain, no, unsafe doesn't really mean, yes, it's definitely unsafe. It means something else. And that goes off, right? So yeah, so unsafe bindings are unsafe only because you're calling into the C API. It's simply declarations of your C functions. And the way you do it in Rust is saying, hey, I'm calling into C. I know that can be dangerous, but I know what I'm doing. Thankfully, this can be generated using bindgen. And I will go to the next slide and then come back to the link. So some things to be wary of. threadx can be configured with a user-defined tx-user.h. So you can add some influence the build flags using a user-defined tx-user. Pretty nice. So you have to make sure that works. And more importantly, you need to intercept what the compiler gets because of these flags. You could have different defines. You could have different include parts. You can have different source parts. So you have to find a way to intercept that so that you can use that in your bindgen. Thankfully, CMake offers this compiler wrapper feature. So it's very simple to write your own little script, which CMake will call instead of calling the compiler. And then you take those parameters out, shove it in a file, and then you call the compiler. And that way, you can intercept all the compiler flags, include directives, save them for later use, and then take all that, pass it on to bindgen. Bindgen basically takes the same flags as the compiler in terms of includes and hash defines. And then you would generate the code. And by doing this, you can generate a code which exactly matches the C API, the C header code, whatever was configured. So, so here's an example of the launcher script. If I can find my mouse. Yeah. It's super tiny script. It's just a shell script which echoes the entire command line into a file, which is in the out directory. And then you execute that command line. And then what you have at the end is just a whole bunch of command lines which you can parse later on and figure out what you should pass into the code gen, bind gen. You can also deal with all the different configurations of threadx. For example, here the code is just checking the target type of Rust, and based on the target type of your cross-compilation, as mentioned yesterday, Rust is great at cross-compilation. So you simply give the target type, and based on that, you decide which threadx build CMake you want to kick off. Okay, some loose ends. Bindgen usually catches the constants defined using macros. Unfortunately, threadx uses macros with the brackets around them, like that, and then Bindgen thinks, no, that's too complex for me. I can't deal with it. Right now, there is this list of constants which are part of the API, which I had to hand code. But I think, with some work on Bindgen, we should be able to solve this pretty easily. But I don't know enough of Bindgen to even attempt this. So just wrote it by hand. It's not much. It's a small list of constants. But that's the only handwritten, let's say, part of the API. Everything else is generated. OK, now you have your application. You have your sys library. And you're pretty much ready to start using threadx. But you would start, and this is how I started, just call the unsafe generated API and try to figure out how the API works, do all the gluing. There's some low-level initialization you can do. In threadx, it is done by some assembly. But in Rust embedded, you already have the Rust embedded ecosystem. You can actually call into that infrastructure to initialize your low-level hardware. And you can fire off your first task, and then it should work. And it did work. And that's when you start thinking about, OK, how can I make life easier for the application developer? How can I make this API nicer? And you start thinking about this Rust threadx-rs crate in the middle, through which you then make the call to the sys crate. And so let me just open up this. What do you mean by? I can see it here. Rusty API. So this is an example of application. And for example, oh, that's the build.rs. My apologies. Yeah. So you see, byte pool allocation, memory allocations can be made, and these task one memory are wrapper types around the memory, and you can't reuse them by mistake. So if you pass this memory into some initializer, that's gone. Oh, sorry. Is that better? Thank you. Oh, so maybe a quick, yeah, I'm good at time. So you have a low level in it. That's the threadx way of doing things. There's a low level initialization callback, and then there's the application callback. The low level init, you call into your board specific or CPU specific low level init, and here it's basically calling into Rust embedded initialization. And then you have the application definition, which is creating all these static application structures, your threads, your mutexes, what all you want to use, you have to create here, and they're statically defined. I think you can also do it dynamically, but the threadx way is a complete static definition of your application. So nice Rust API. So you can start benefiting from the ownership model. There's no way I can create a block pool or a byte pool. I pass it to one task. There's no way I can pass it to another task because that's gone and consumed. So simple mistakes are easy to make in C. It's not possible here. So that's what we mean by a rusty API. It improves that experience and catches the errors at compile time. And yeah, you can do that. OK. This is a very basic wrapper. Honestly, this was a Christmas vacation project. So it's really quick because the tools are great. Things just work. And I was very surprised when I was able to do the glue to connect the callback into the closure. And so testing with, I only use this because that's what I have available at home. So somebody is interested in trying out different hardware. The Rust embedded ecosystem supports so much more hardware. It'll be interesting to see if that'll work. threadx also supports them already. threadx-sys, I don't like this hand coding, even though it's a little bit. I would like to find a solution for that, because then it would be purely generated binding. And then, yes, there's a bit of unsafe in there. And unsafe is scary. And good to have few eyes look at it and see what could be wrong there. More examples in documentation. There is some example hello world application. There's a Q application which I will run. And controversial take is it's nice C code, no macros. It could be an interesting candidate to try and convert using C to Rust and make it a pure Rust project. Worth giving a shot. But then you get disconnected from the threadx project. So that's why it's a bit controversial, because then it takes a life of its own. Do you want to do that or not? Because like I said, threadx does have a lot of wisdom of the ages baked in there. You may not want to lose that. OK, so pray to the demo gods. Deferred formatting for logging, it's using ST-Link debugger. And this is the default Rust embedded tooling you would use if you want to do this on your own. ProBRS is flashing. The image is about 19 kilobyte, this test image. And this is using the event flag mechanism of threadx, which is there's a timer. And then the timer is messaging, three threads. Yeah, it's thread 1, thread 2, thread 3. So it's like a broadcast event going out to all 3 threads. I think a nice, if somebody is familiar with ZBus in Zephyr, this could be a nice mechanism to implement a ZBus kind of system in Rust. That'll be nice. So another demo, I'll show you the code of the demo as well shortly. So the other demo is Q. So it's around the same size. Here is just one thread, and it's 2 threads, one thread sending a message to the other thread. And what's interesting there is it's got a typed channel kind of interface. So I showed you the allocation earlier. Oh, by the way, there's also a global allocator, so you can use new, and you can assign a block of memory and give that to the global allocator. So you can do all the static definitions of your areas, And then you can also have a global allocator. So in this case, total heap is 12 kilobytes. First 2 kilobytes is allocated to this block pool. And within that block pool, I'm allocating three memory blocks for the two tasks. One 256 for task 1, another 256 for task 2, and then 64 bytes for the queue. And then here, this is what I meant by a typed channel interface. So I'm creating a queue of type event. Event is just an enum on top. You can use enums in embedded. That's the best part. So you can send enums over this channel interface. And it's a type channel interface. So you get this channel of type event, and you have another channel of type some other event. You can't mix them up. That's compile time checked. Yeah, I think that's it. I have left some time for questions. Yeah, thank you so much for listening.
Thank you, Sojan. We have one question over here already. You also really built in some suspense in your presentation today.
Thanks for the great talk. How long did your journey so far take?
You mean for this or for Rust?
For building the Rust buildings from the very beginning, adding threadx support to Rust up to the point where you are today?
For this project, most of the work was done during 1 week and during Christmas. And then maybe last week for this talk, just cleaning up a bit. Actually, it's not much because everything just comes in. If you look at the code, there's really not that much. And it's on GitHub. I think I had a link. Yeah, it's all available on GitHub. Please take a look, play around. If you'd love to contribute, that'll be great as well.
Yeah, thanks a lot for the talk. Over here. So one thing I was wondering about, you said you have the threadx-sys grade with the generated bindings, and then you review kind of how can you express it in more Rusty APIs, taking into account ownership and so on. Did you find any, maybe not weaknesses, but inconsistencies in the existing architecture in C that are only exposed by taking a view from an ownership perspective, or not at all because it's so well matured that any issue that would be uncovered by ownership like searched long before?
I don't think I've spent enough time on it to comment, but in general, the threadx way is complete static allocation of your application. So all your application handles, the memory handles, the byte pool handles, they are all statically allocated, right? So it's easy to borrow from them. It's not going to move. It wasn't too bad. There is just one issue I'm having with the timer, because the timer expects a callback. Unfortunately, that callback doesn't take a void star pointer to shove some context in, and I don't know how to solve that yet. So right now, it's a bit ugly. Yeah.
So then I have a question. Are you doing Rust? So you said that this was a Christmas project. So are you working in Rust at Axia?
Yes, we do work. We do Rust work at Axia. We are working with some tier 1s and OEMs to try out Rust in some context. Yes, we're also building an automotive platform with a lot of Rust in there. That's more of an R&D project.
Yeah, great.
Thank you for that question. Yeah.
Yes, thank you, Sojan. Thank you very much.
Thank you.